In this lecture, we're going to continue our discussion of numerical solution of eigenvalues. In the previous lecture, we discussed using the power method and inverse power method to solve for the single eigenvalue. That is either the largest eigenvalue of the system in the case of the power method, or the closest eigenvalue to some initial guess in the inverse power method. In those methods we talked about, after you solve for that, you could use a deflation technique to continue to solve for the other eigenvalues, but mentioned that it's not the most numerically stable of solutions. So today we're going to talk about a method where we can solve for all the eigenvalues, and in order to do that, we're going to need a few tools along the way. And so the first thing we're going to talk about is a couple of those sort of tools or transformations, the first of which is called a householder transformation or householder method. So first thing I want to say is that two matrices are similar. So I'm going to give a definition when I'm talking about matrices. A is similar to B when they have the same eigenvalues. And so what the householder method does is seek a matrix B that is similar to A, that is, it has the same eigenvalues of A, except the matrix B will be a tridiagonal matrix. So it'll have that special structure. Now, the way we do that is we start with a matrix P that's equal to the identity matrix minus 2 omega transpose, or these omegas are a vector, and it has this constraint, omega transpose is equal to 1. And with that, what we'll do is seek a series of matrix A, which will eventually converge to a tridiagonal matrix, that is B, or one that's similar to A, by taking a series of iterations. Again, we're using the superscripted parentheses to indicate an iteration. So we'll form a matrix P1, apply this multiplication to the matrix A to get the new matrix A. And the new matrix A, we require, now this is a constraint, we require that for all rows below 2, then the first column, this 1 will correspond to the iteration here, but the first column will have all zeros. So it turns out that these two constraints, or this constraint plus this thing, will give us an idea of how to solve for the components or find the components of omega. Now the details of that are kind of long for a lecture, so we're going to omit them for now. But that's the idea, and the details, you will see them in the pseudocode later, but we won't discuss them here. Okay, so this condition plus this one adds constraints that allow us to solve for the components of omega. And then we can apply this transformation. And if we continue to do this, so if we apply it for one the first time, again, we will have a matrix that has this kind of structure. And then what we can do is basically ignore those rows and apply the transformation to the remaining matrix. And this will continue. So we'll continue to get zeros here, and then we'll ignore those and apply the transformation again and continue. And eventually, after k iterations, the matrix will become tridiagonal. And so that's just the idea here. So we continue these transformations, and ultimately we end up with a tridiagonal matrix. So again, the pseudocode for householder method is here. It's a little bit long, and I don't want to go through all the details in this lecture, but it's available in the notes for you to see. But again, what we're going to do now is kind of leave this for momentarily, and we'll come back to householder's method in a minute. So the second tool we need then is something called an Orphan normalization process. And what we'll do is use the Gram-Schmidt method for that. So in order to give an idea of what this does, Imagine you have a matrix A, and we'll look at the 3 by 3 case, but this generalizes to higher dimensions. So if you have the 3 by 3 case, it's nice because we can imagine that you have 3 column vectors, A, B, and C, and we could sort of imagine those, and maybe let me draw them sort of more skew to overemphasize the point. But we could imagine these vectors in space like this. So say A, B, and C. So 3 vectors. And I've intentionally drawn them very skew. And what we're sort of seeking to do is to find a rotation and scaling. We'll call that, say, R. A rotation and scaling that will take those 3 vectors and turn them into orthogonal unit vectors, or what we call orthonormal, right? So the orthogonal means that they're at right angles to each other, and the normal part of the word just means that they're unit vectors. So then we have 3 unit vectors, Q1, Q2, and Q3, that are at right angles to each other, right? So it's said that the Qs, Q1, Q2, 3, are the orthonormal basis of A, B, and C. And instead of actually solving or trying to find this rotation and scaling matrix, there's actually a method for finding the orthonormal basis directly, and that process is called the Gram-Schmidt method or Gram-Schmidt process. Okay, so the first thing we'll do is easy. We'll just find the unit vector of A, right? And we'll call that Q. So the next thing we'll do is we're going to subtract away the projection of B onto Q, right? So again, if we have sort of if we have 2 vectors, say a vector B and a vector Q1, and then we want to know the projection of B onto Q1, well then we compute that with Q1 TB times Q1. And so then, if we want to subtract away the component, the part of B in the direction of Q1, then we just do this operation here, and we'll label that uppercase B, which then we can just simply compute the unit vector of it, and we'll call that Q2. And so now we have a Q1 and a Q2, and then finally we'll do a similar thing with respect to the C direction, in this case subtracting off the component of C in the direction of Q1 and the direction of Q2, labeling that uppercase vector C, and then just dividing by its magnitude to define a unit vector Q3. And so the 3 of these things define the orthonormal basis, Q1, Q2, Q3, and we can put that in a matrix form that we'll call Q. Again, this process is called the Gram-Schmidt process. And here's the pseudocode for that. That does generalize to higher dimensions, and that was the case with the pseudocode there. You had n number of vectors. So then a QR factorization would be, if we start with a matrix A, we can decompose it into Q and R, where Q is this orthonormal basis and R is that sort of rotation and scaling matrix. And finding R, once so we'll find Q with Gram-Schmidt, and then once we know that, we can simply, if you look at this equation, if we multiply on the left-hand side by Q inverse of both sides of the equation, well, this becomes the identity matrix. And so we can find R just simply Q inverse matrix multiplication A. The nice thing about orthonormal matrices is that their inverse is their transpose. So normally to find a matrix inverse is an expensive computation. But in this case, because Q is orthonormal, we just simply take its transpose, multiply the A, and we have R if we'd like to have it. So that is the QR factorization. And for our 3 by 3 case with matrices A, B, and C, this is what R would look like in that particular case. So we can use this QR method for computing the eigenvalues of a matrix, and in fact, computing them all at once. And it's kind of scary how simple this algorithm is, because what we're going to do is we're going to do a QR factorization of A, and then we're simply going to reverse the factors and multiply them together. And so that literally we just reversed the R and Q matrix and multiply them back together, and we get a new matrix A1, and then we would continue to do this K times, right? You know, the number of iterations times. It turns out we can do this because the matrix A1 and A are similar. We can prove that quite easily by looking at this type of thing, and let's see what we did here. First thing is, let's just start off with the first equation. The first equation is embedded in here. If you just look at it, it's you know, A0 QR0, you know, 0, the first iteration. And then what we're going to do is just multiply on the left-hand side of both sides of the equation by the inverse of Q0, and on the right-hand side by Q0. And then over here, if you look at this, so we just did the same thing to both sides. We multiply on the left here and here, multiply on the right here and here. Well, then we have Q0 inverse times Q. That's the identity matrix. And so that just leaves R0, Q0 equal to A1. So we verify that this is something that's okay to do. These will have the same, the A1 will have the same eigenvalues of A. And in fact, as we proceed down the iteration, once we get to AK, this matrix will have a tridiagonal structure with the eigenvalues on the diagonal. And if we can just use this algorithm just like it is, but there are a couple of things we can do to speed it up. One of them is we'll use what's called the shifted QR. So we'll, instead of doing the QR factorization on A, we'll do the QR factorization on A minus a constant alpha times I. And there are various procedures for finding that constant alpha. In fact, they're included in the pseudocode later. But nevertheless, once we do this, then we can reverse the shift in the similar fashion. So reverse the factors Q and R, and then just add in this guy. And what that will do eventually is lead to a matrix that has this kind of structure. So we won't worry about what all of these, but the lower diagonal value will be the first eigenvalue of the system. This epsilon will be a very small number. And in fact, we can use this epsilon to stop our iteration. So basically, we'll look at this value, and if it's below some tolerance, we'll accept this as the first eigenvalue. Then we'll deflate by crossing out this row and column, and we'll do it on the remaining substructure. And in fact, we'll do it on down till we have a 2x2 matrix, in which case we have an explicit formula for the eigenvalues, and we'll use them. Turns out that explicit formula for the eigenvalues can also be used to determine alpha, because the typical procedure for determining alpha is to just compute the eigenvalues of the lower in 2x2 matrix in the lower right-hand corner, determine which of the two eigenvalues of this are the largest, and that becomes, the smallest, and that becomes your shifting factor. If you need to know the eigenvectors, you're one step away with the inverse power method from getting them, right? Because now we have the eigenvalue. We can put that into the inverse power method, and in one iteration, because we're already sitting on the eigenvalue, we can compute the eigenvector. The other thing we can do to speed up the QR method for solving for the eigenvalues is to start with a tridiagonal matrix. So it turns out that the QR decomposition takes like order n cubed. However, if we start with a tridiagonal matrix, we can do it in order n. And so therefore, the combination of the shifted QR plus starting with a tridiagonal matrix can give us a very fast convergence to the eigenvalues. How do we start with the tridiagonal matrix? We use the householder transformation. So that's where that comes in. So we would start with the matrix A, apply the householder transformation to it to get a similar matrix B that is in tridiagonal form, and then apply the QR method for solving for the eigenvalues. So then we have the pseudocode for the QR algorithm. Again, we're going to start with the tridiagonal matrix, and with that, because we start with the tridiagonal matrix, it's possible to simplify the QR algorithm such that we do the QR decomposition implicitly row by row and solve for the eigenvalues sort of in that way without doing all the matrix multiplications, which can be expensive. And so this is the algorithm. It's kind of long, too long to go over in detail here, but it's in the notes if you'd like to see it.